Hello everyone, welcome to my presentation titled Detection of Rogue Devices using Unintended Near and Far Field Emanations with Spectral and Temporal Signatures. I am Mohammed Faizul Bari, a third year PhD student in Electrical Engineering at Bari University, working with Professor Shreyas. This is the outline of my presentation. First, I will talk about the motivation behind our work. Then I'll briefly discuss the relevant theory of monopolar antenna. Next, I'll talk about our experimental setup and data collection. Then I'll talk about the near and far field emanation pattern and the corresponding spectral and temporal signature associated with it. I'll use spectral signature to detect the presence of a rogue device in a secure facility. And finally, I'll conclude my presentation with a brief summary of my work. So first, let's talk about the motivation. So what is emanation? It's unintentional electromagnetic emission from electronic devices. These devices are not designed for this kind of emission. For example, here we have an Arduino Uno, which is not supposed to transmit RF signals during normal operation. Still, if we put a probe on top of it, we'll find some signal peaks in the spectrum analyzer. This is emanation from the Arduino. Emanations can reveal cryptographic information, which is the basis for side channel attack. So it's a serious vulnerability of electronic devices. Initial studies of emanation are on high-power devices of that time, which is less relevant now for our current low-power electronics. Also, most studies, both classical and latest, focus on devices with a specific operating frequency. Complex systems, such as desktop or laptop computers, have both low and high-power components operating at different frequencies. For example, CPU, GPU, RAM, etc., all of them have different clock frequencies. Hence, characterization of emanation pattern for such a modern, complex electronic device is required. And that's what we have explored in this work. Before going into the details, let's look at the theory of monopolar antenna briefly. The whole radiation zone can be divided into three regions: reactive near field, radiative near field, and far field or Fraunhofer region. Radiation decays as 1 over r cube, 1 over r squared, and 1 over r in these regions. The region boundary equations are mentioned in the figure. For high frequency, say 3.5 GHz, lambda is short. The near field will be in millimeter range, which will be very difficult to observe. Hence, we observe the near field at 264 MHz. From these equations, we calculate that reactive near field boundary is 8.8 centimeter and radiative near field boundary is 14.15 centimeter. Now that we're familiar with the motivation and background theory, let's investigate our experimental setup. So we have used an off-the-shelf desktop computer as our target device, which you can see here. It has an Intel Core i7-6700 processor with a base frequency of 3.5 GHz and 8 GB RAM operating at 2400 MHz or 2.4 GHz. The whole setup was put in a 12 by 12 feet anechoic chamber. For far-field emanation detection, we have used a sliding antenna that you can see here. It can move from 35 centimeter to 235 centimeter distance from the target. For near-field observation, we have used an EM probe that can go as close as 1 centimeter. The probe is placed at different heights on a stand, and the output goes to a spectrum analyzer through a 40 dB wideband amplifier. Based on our initial scanning of large spectrum covering from DC all the way up to 4 GHz, we chose three frequencies of interest: 264 MHz, which we postulated to be coming from the motherboard traces, 2.4 GHz that's coming from the RAM, and 3.5 GHz that's coming from the processor. Now that we have collected data, let's look at the emanation pattern. Both plots show near-field emanation power versus distance in the blue curves. In figure A, we have fitted 1 over r cube curve, the red curve here as you can see, which fits nicely up to 9 centimeter and starts deflecting after that. In figure B, we have fitted a 1 over r square curve, which fits closely from 10 centimeter onward. So experimentally, The boundary between reactive and radiative near field is somewhere between 9 to 10 centimeter, which matches closely with our theoretical value of 8.8 centimeter. Inset here shows the emission spectra versus frequency at 4 centimeter distance. Now, for far field emanation detection, we have used similar logic. We observed far field at high frequency, that is 3.5 gigahertz, so that the near field is limited and the far field can be observed better. For 3.5 gigahertz, our calculation shows that far field begins at 43 centimeter. The emission power versus distance plot, again the blue curve, shows 1 over R trend that is shown in the red curve. So the fitting matches not that closely as compared to the near field region, but it's close within experimental error range. Insert shows the emission spectra versus frequency at 40 centimeter distance. Okay, now we will look at the spectral and temporal signature. Here, the plot of emanation power versus frequency shows that power is significantly high at low frequencies for all the distances. Each color represents a specific distance, as I mentioned in the legend here, as you can see, from 35 centimeter all the way up to 235 centimeter. Also, emanation power reduces with distance as we have seen earlier. So you can see from red, which was 35 centimeter, to purple, which is 235 centimeter, the emanation power reduces. Another important observation is that emanations have a frequency cap for detection range. For example, at 235 centimeter, we cannot detect emanation at 3.5 gigahertz. So 3.5 gigahertz is detectable up to 200 centimeter. So lower frequency components can be detected even in further range. Another interesting phenomena was that the peaks were shifting with time. As you can see here, t equals to 0, the PC is just turned on and there is no peak. So we were just observing noise. We see a peak at 0.5 second, which then shifts left at 1 second. It gradually keeps shifting with time, as you can see at 1.5, 2, and 2.5 seconds. Here, the emanation plots are stacked on top of each other for better visualization. Each color represents a specific time. For example, the gray here represents 0.5 second, red represents 1 second, blue 1.5 second, and so on. The legend is shown here. So time is basically flowing upwards. And you can clearly see the peaks are shifting towards left. So this peak shifting is actually related to the program that is running inside the PC. So based on that, we can characterize the program, and it has many different applications. For example, malware detection inside a program. Now that we know near and far field emanation pattern and their spectral and temporal signature, we'll use them to detect our rogue device in a secure facility. So the idea is that in a secure data center or cloud server, we have an RF baseline with existing emanations, as I have shown bottom here. So this is our secure facility. This is the RF baseline with existing background noise and other emanations and overt signals. If a new device is introduced in the server room to steal it, the RF baseline changes and shows a new peak, as you can see here. So this peak is related to the new device, and based on the presence of that new peak, we can detect the presence of a new electronic device in the server. So whenever a new peak occurs, we can say that there is a new device introduced there, which wasn't supposed to be there. So we can detect the presence of the rogue device. To that end, we have first processed our signal with Savitsky-Golay filtering to smooth out the noise, but keep the peak intact, as you can see here. In both of these figures, the blue and red show before and after filtering curves. So you can clearly see the blue one showing significant noise, whereas the noise is somehow smoothed in the red. So these, after removing the noise, this is then fed to a peak detector to find any new peak. This method works both high SNR, as shown in the left figure, which where we have 82 dB SNR, and also it works for low SNR, where we have 18 dB SNR in the right figure. In both cases, the span was 5 kilohertz and the resolution bandwidth was 3.9, and for left one it was 3.3 hertz. So using our method, first removing noise and then detecting peak and then comparison with the existing baseline, we can detect the presence of a rogue device in a secure facility. So now I will briefly summarize my presentation. We have characterized um, the emanation pattern from an off-the-shelf desktop computer. We have explored both near and far field and showed that the emanation pattern matches that of a monopolar antenna. Next, we have explored the spectral and temporal signatures, and using the spectral signature with a peak detector, we have detected the presence of a rogue device in a secured facility. So that's all in my presentation. I'll take this opportunity to thank my co-authors, Meghna Roy Choudhury and Vaibhav Chatterjee. Also, I'd like to thank the funding organization for this work, IRPA. Um, so with that, I'll conclude my presentation. And if you have any question, please feel free to ask. Thank you.